This is section 4.2 notes, and we start with indeterminate forms. Now, there's lots of indeterminate forms, but what we're going to focus on today is 0 over 0. So we have indeterminate form 0 over 0. Functions f of x and g of x are both 0 at x equals a, then the limit as x approaches a of f of x over g of x cannot be found by substituting x equals a. The substitution produces 0 over 0. So if you get 0 over 0, it says a meaningless expression known as an indeterminate form. Our experiences so far have been that limits that lead to indeterminate forms may or may not be hard to find algebraically. It took a lot of analysis in exercise 77 of section 1.1. Oh, you guys probably totally remember exercise 77 in section 1.1 to find the limit as x approaches 0 of sine of x over x. Oh, we certainly remember that. The limit as x approaches 0 sine of x over x is 1. And if you remember the graph, it does this. But we have had remarkable success with the limit used to calculate derivatives, which always produce the equivalent of 0 over 0. L'Hopital's rule enables us to draw on our success with derivatives to evaluate limits that otherwise lead to indeterminate forms. So if you get the 0 over 0, L'Hopital says just take the derivative of the top and the derivative of the bottom. Here we have example 1, indeterminate form 0 over 0. Estimate the limit graphically, then use L'Hopital's rule to find the limit. So this graph seems to be leveling out to, how about 0.5, a half. So that's the graph of it. So we're expecting this to be a half. But if we plug 0 in right away, we get square root of 1 minus 1 over 0, which is 0 over 0. Now that's an indeterminate form. Now the limit still could not exist, but it could exist. As a matter of fact, I think it's going to end up being 1/2. Well, L'Hopital's, we're going to say, hey, we're using L'Hopital's here. Limit as x approaches 0 of, now the derivative of the top is 1/2, 1 plus x to the negative 1/2, times the derivative of the inside, which is 1. Now the derivative of the bottom is 1, so we have the derivative, over 1. Now we can plug 0 in, and I think we're going to be fine. We have 1/2 of the square root of 1 plus 0, which is equal to 1/2, and that's exactly what this graph is leveling out to as we approach infinity. Let's look at example 2, and it's a little more complicated, but it's very similar. Let's plug in 0. Square root of 1 minus 1 is 0, minus 0 over 2 is 0, and 0 squared is certainly 0. So now we have an indeterminate form, which means we can use L'Hopital's. Now you have to be careful, because if you don't have an indeterminate form, you cannot use L'Hopital's. All right, but we have an indeterminate form here, so we're going to use L'Hopital, so we're going to indicate that. Limit as x approaches 0 of 1/2, 1 plus x to the negative 1/2, and then that's going to be minus 1/2 right here. The derivative of negative 1 is 0 over 2x. Now if we plug 0 in for this, we get 1/2 minus 1/2 over 0. We get 0 over 0 again, but that's okay, because now we have another indeterminate form, and we can just use L'Hopital's again. We have the limit as x approaches 0 of negative 1/4, 1 plus x to the negative 3/2 times the derivative of the inside, which is 1. Derivative of negative 1/2 is 0 over 2. Now we're going to plug 0 in. And when we plug 0 and we get 1 to the negative 3/2, this part is just 1. We get negative 1/4 over 2, which is negative 1/8. Note, in order to use L'Hopital's rule there, the form must be indeterminate. The form must be indeterminate. Okay, here we go. So limit as x approaches 1, that'd be 0 over, that'd be 0 over 1. So that's 0. On this one, we'd have the 1 over 0, which is really infinity. And then here we'd have 0 over 0. This is the one where we can use L'Hopital. So notice that, don't automatically think that you're just going to be able to use L'Hopital's every time. You can't use it on this one. You can't use it on this one, because it already has an answer. It's not indeterminate. This one's 0 over 0. We would continue on and use L'Hopital's. Or you wouldn't have to do L'Hopital's on this one, because it factors. So x minus 1 over x plus 1, x minus 1, and that goes to limit as x approaches 1 of The x minus 1's cancel out. 1 over x plus 1. Plug the 1 in. That would be 1/2. Using L'Hopital's rule with one-sided limits, evaluate the following limits using L'Hopital's rule. So if we plug 0 sine of 0, 0 over 0, we get an indeterminate form. So we have, we're going to do L'Hopital's. Limit as x approaches 0 from the right of cosine of x over 2x. Now when we plug 0 in, we get 1 over 0, but we're on the positive side of 0. So this is going to be positive infinity. Now we have the same thing here. So when we use L'Hopital's, we get limit as x approaches 0 from the left, which is, we have cosine of x over 2x, but now we're on the negative side. And so now we're going to take a 1 divided by a very, very small number, or a number very close to 0, but on the negative side. So it's like we're dividing by cosine of negative 0.000000001, something very small. But now we're on the negative side. So this is negative infinity. Now let's see if that's actually happening with our calculator. Let me clear all this stuff out. Sine of x over x squared. So we have sine of x divided by x squared. And let's see if we're in radians. We are. So let's go zoom 6. Now we're looking at 0, very close to 0. And on the left side, on the negative side, as we approach 0 from the left, it's going down to negative infinity, like we said. And 0 from the right, we're going up to positive infinity. All right, use L'Hopital's rule to find each limit. Now on this one, I wouldn't go to L'Hopital's right away. I'd multiply the top and bottom by 3. So we get that sine of 3x over 3x. That part is 1, so the answer should be 3. But if we plug 0 in right away, sine of 0, 0 over 0, we get an indeterminate form. So we're going to use L'Hopital's. Limit as x approaches 0 of 3 cosine of x over 1. And now when we plug in 0, we get 3 times 1, and we get the same answer. We get 3. How about one where we're throwing in thetas instead of x's? That's the only real difference here. If we plug in pi over 2, sine of pi over 2 is 1, and cosine of pi is negative 1. So we get 0 over 0. L'Hopital's limit as theta approaches pi over 2 of negative cosine of theta over, what's that going to be? Negative 2 sine of 2 theta. So cosine of pi over 2 is 0, and sine of pi is also 0. So we get 0 over 0 again, which means we get to use L'Hopital's again because we ended up with an indeterminate form. Now let's denote that with L'Hopital's. And let's make that positive. Cosine negative sine of theta over 4 cosine of 2 theta. Now we're going to plug pi over 2 in. Sine of pi over 2 is 1. We get negative 1, and cosine of pi is negative 1. So we end up with an answer of 1/4. Discuss graphs of secant, cosecant, tangent, natural log, inverse tangent. So this one, we start out with graphing cosine. So this must be the graph of secant. Now we need to familiarize ourselves with these graphs because you might be asked to evaluate the limit as x approaches. Let's say this would be pi over 2. Pi over 2 from, we could say from the left of secant of x, and we would know that that goes up to infinity. Or we would need to know the limit as x approaches 0, 0, of secant of x. Secant of x, that's equal to a positive 1, or the limit as x approaches pi of secant of x, that's equal to negative 1. This one is cosecant. We could ask limit questions about this. Well, that's sine. So then we turn that upside down, and that ends up being, what did I say it was? Cosecant. Yeah, because this is sine. This is tangent. So we would know that we would have to know limit as x approaches 0 of tangent of x is equal to 0 right there, or that if we approach pi over 2, that's headed up to infinity, pi over 2 from the left. This is cotangent. We could ask limit questions about this. This one's a big one, natural log of x. The limit as x approaches infinity of natural log of x does approach infinity, but it approaches very slow. Inverse tangent. The limit as x approaches infinity of inverse tangent is pi over 2. Because now right here, if this is pi over 2, and let's say up here at 1, then now this is going to be the pi over 2, and this is the 1. So as x approaches infinity for inverse tangent, this is leveling off to pi over 2. All right, well, here's some questions about some trig functions. Limit as x approaches 0 from the left of tangent. This is going to be 0 over 0. So now we have the limit as x approaches 0 from the left of secant squared of x over 1. And secant of 0. Which one is secant? This is secant. Secant of 0 is actually 1. So this ends up being 1 over 1. The answer on this one is 1. How about from the right? Oh, and I want to denote that I used L'Hopital's on this. So L'Hopital's on this. Well, we get 0 over 0 again right here. We have the limit as x approaches 0 from the right of secant squared of x over 1. Over 1, we're doing derivative. Plugging 0 in, and we get 1 for that one as well. 12, how about over x squared? Well, we still get 0 over 0. So we're going to do L'Hopital's. Limit as x approaches 0 from the left of secant squared of x over 2x. But secant of 0 is the reciprocal of cosine of 0. Cosine of 0 is 1. So secant squared is 1 squared, which is 1. Oh, we get 1 over 0. Now we're going on the left side of this. So the left side of secant, let's see. What do we have here? Left side of, well, it's going to be secant squared, so that's going to be positive no matter what. And here we actually have, negative numbers. So this is 0, but on the negative side. So 1 over like negative 0.00000. Now that's going to create a very big number, but a very big negative number. So this is actually negative infinity. 0 over 0 for this one. So we have an indeterminate form. L'Hopital's limit as x approaches 0 from the right of secant squared of x over 2x. Now that's going to be 1, so that's not an indeterminate form. And then we have 0 from the right, so 2 times something very small, but positive. So that's actually going to be positive infinity. Use L'Hopital's rule to find the limit. Well, first let's decide if we have 0 over 0. We have square root of 9 minus 3 over 0. So we have 0 over 0. Now we're going to use L'Hopital's rule. Limit as x approaches 7 of 1/2 times 2 plus x to the negative 1/2 over 1. Now when we plug 7 in, that's going to be 1/2 times 9 to the negative 1/2. So that's 1 over 2 times the square root of 9, which is 1/6. If we plug 0 in here, we get 1 minus 1 minus 0 over 1 minus cosine of 0 is 1. So we get 0 over 0. Let's do L'Hopital's for this. L'Hopital's limit as x approaches 0 of 3e to the 3x minus 3 over, oh boy, 2x, because that's chain rule, e to the x squared plus sine of x. Now what happens when we plug 0 in? We get, that's going to be 1, so 3 minus 3, 0 over 0 plus sine of 0 is 0. All right, so we get 0 over 0. We can do L'Hopital's again. Probably just have to do this one more time, I would guess. We have the limit as x approaches 0 of 9e to the 3x over, well, that's going to be product rule. So first times the derivative of the second plus the second times the derivative of the first plus cosine of x. Now what happens when we plug 0 in? We get 9 over, that's going to be 0, plus 2, because that'll be e to the 0 is 1, plus cosine of 0 is 1. So plus 1, 9 over 3, we get 3. Let g be a differentiable function. The graph of g prime, the derivative of g is shown below. The graph g prime has horizontal tangent lines at -1, at 1, and at 2. Select values for g of x are given in the table. So there's x and then g of x. Here's the graph of g prime. Evaluate each limit. G of 0 is -1. So we have -1 plus 1 over 2 times 0, which is 0 over 0. So we can do L'Hopital's rule. Limit as x approaches 0 of g prime of x over 2. So g prime of 0, whereas g prime of 0 is 0. So 0 over 2 is the final answer is 0. G of 0 is -1 minus 2 squared, which is 4, over 2 minus 2. So we got -5 over 0. But we're on the positive side, so this is going to be, but it's negative, so negative infinity. This one, what if we plug -2 in? G of -2 is 3. 3 plus 4 over 2 minus 2. So we get 7 over 0, which is infinity. Now we on, yeah, I mean, that'll work. That'll work. What if we plug 1 in? 0 times g of 1. So let's just do this. 0 times g of 1 minus 2 times the natural log of 1 is 0. Well, 0 times anything is going to be 0 over 1 minus 1. All right, so we get 0 over 0. It doesn't even matter what g of 1 is, even though it's 2. We can do L'Hopital's because we have an indeterminate form. Limit as x approaches 1 of first times the derivative of the second plus the second times the derivative of the first minus 2 over x over 3x squared minus 1. Now let's try to plug 1 in. We get 0. What's g of 1? G of 1 is 2. All right, so we get 0 times g prime of 1, which is 1. So we get, what do we got here? 0 times 1. We get g prime of 1 up here. We'll just call it 1. Plus g of 1. G of 1 is 2 over 3 minus 1. All right, we get 2 over 2. Oh, that's 1. Limit as x approaches -1 of g of -1 squared. G of 1 is 2. So we get 2 plus -2 over natural log of 1 is 0. All right, we get 0 over 0 for this one, so we can use L'Hopital's. Limit as x approaches -1. I can scroll down here a little bit. Oh boy, we get 2x g of x squared. So we get derivative of the outside, g prime of x squared. Derivative outside times derivative of the inside, plus 2 over 1 over x squared, but times the derivative of the inside, which is 2x. Let's see what we get when we plug -1 in here. We get -2 g prime of 1. G prime of 1, we'll call that 1. It seems close. Plus 2 over 1 times -2. Right? Yeah. So that's going to be 0 over -2, so the answer is 0. Describe each if x of t represents position, v of t is velocity, and a of t is acceleration. So if we integrate from 4 to 10, 1/6 times x of t, I would call this average position. S of t, yeah, x of t represents position. Oh, why do I have s? I don't want s of t here. That's a typing error. Let's fix that. Let's try to fix that. I didn't use s for position. I used x. So x. Oh boy, what happened? Here, we'll do it like that. X. Why is a double vision here? Ooh, there's a whole bunch of them. Delete, X. Finally got to it. This would be average velocity. After all that, average velocity. This is also average velocity, but let's investigate this. Average velocity. If we integrate velocity, we get position. So this becomes 1/6 times x of t from 4 to 10. So you end up with x of 10 minus x of 4, but then 1/6 of that divided by 6, which is exactly what we get here. So this is average velocity, and this is average velocity as well. This would be average acceleration. This right here is also average acceleration. And imagine, if we did the integral of acceleration as velocity, so that's 1/6 velocity evaluated from 4 to 10. So that'd be v of 10 minus v of 4 over 6, which is exactly that right there. This would be average jerk. Use a calculator. All right. If natural log of 1 plus x squared is the antiderivative of f of x, find the integral from 1 to 3 of f of x. Well, it says this is the antiderivative. So it's natural log of 1 plus x squared from 1 to 3. So natural log of 10 minus natural log of 2. And I guess we could use a calculator for this, but whatever decimal value that would be. I guess it says use a calculator, so we might as well finish it. Natural log of 10 minus natural log of 2. So 1.609. 1.609.